Hello and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, physics based perspective. This is lecture number 25 and the topic of the lecture is introduction to semiconductor heterostructure. So, in this lecture we will be looking into the various metal semiconductor junction and semiconductor junction. So, why this lecture is important or why this understanding is important is in most of the cases you will have the last line should be a metal line which will carry the signal from the device to a higher level, where say for example you are designing any circuit, the current flowing through the device will always be carried by a metal to the external world. So, you have levels of metallization occurring in the system. Now, the understanding of the metal semiconductor junction is important to understand the behavior of the current versus voltage characteristics of this device. Now, out of which we have three effects which come into picture. One is known as the Schottky contact, which we will study. We will study Schottky effect and obviously the Schottky contact because of that, and then ohmic contact, and then we will look into semiconductor junctions, within which we will be studying homojunctions and heterojunctions. Ohmic contacts primarily are that these are basically low resistance junctions both in the forward and the reverse direction, right. So, even if you move from point A to point B across the junction and if you measure the resistance, then it is almost the same as the resistance moving from point B to point A, right. So, across the junction the resistance value is almost the same. Now, within the homojunction and heterojunction I will tell you what does it mean. Both are basically semiconductor junctions, but the nature of the semiconductor on both sides of a homojunction is the same, whereas for the heterojunction it is different. We will come to that as we move ahead in the understanding of our these metal semiconductor and semiconductor junctions. Now, let me come to first of all the metal semiconductor junction. Now, when a metal actually contacts a semiconductor, a barrier is formed which is known as a metal semiconductor barrier. I will try to explain it through a graph. And so, what we were doing is, as I discussed with you, that you will have ohmic contacts and you will have non-ohmic contacts, right. So, we will take each one of them individually and see how it works out. But one important factor which is prevalent across the network is that when you have a metal and a semiconductor contact, then you always have this barrier formation taking place, right. And this barrier formation does not allow the carriers to move very easily from one part to another, because of obviously this barrier basically is an energy barrier, right. That is what we refer to as the barrier contact. So, just to showcase one barrier contact, let me draw for you a metal semiconductor contact, an n-type semiconductor. And if you remember, my n-type semiconductor characteristics is basically Fermi level is very close to the conduction band, and less is the distance between conduction band. So, less is the energy difference between Fermi level and conduction band, more it is n-type, semiconductor. What does it actually mean? It means that lower the value or smaller the difference, which means closer the Fermi level is to the conduction band, then more will be the doping, more will be n-type, and the reverse is true, that if the Fermi level is very close to the valence band, it will be more of a p-type, right, that we have already studied in our basic understanding of semiconductors. And if it is exactly in the middle, it is almost like an intrinsic semiconductor. In that case, EF is equals to EFI. EF is the Fermi level and that EFI is basically the intrinsic Fermi level, and they will coincide with respect to each other, right. Otherwise, there will be a gap between EF and EFI. EFI is known as the intrinsic semiconductor, intrinsic Fermi level. We also have learned from our previous discussions that Fermi level per se, if you do not apply any bias, will be always aligned. the variation of Fermi level with respect to x, the distance, will be 0. So, at equilibrium when you do not apply any bias, no bias condition, let us assume there is no bias condition, then my EF dEF dx will be equals to 0, which effectively means that the Fermi level will remain constant across the junction and there will be no flow of charge carriers from point A to point B. However, if you apply a bias, then there will be a discontinuity in the Fermi level that will result in the charge carrier concentration difference, and therefore, that will result in a current. Just highlighting all those issues here at this particular point. Let me draw for you a metal, right, metal and an n-type semiconductor. An n-type semiconductor I am doing. So, let me draw for you, this is the metal contact here. So, this is the metal junction, this is the Fermi level which you see EF, let me name it as M, EFM, and this is my vacuum level here, and the Fermi level is EFI is aligned, of course, right. So, this is aligned, and of course, since this is an n-type semiconductor, my EC will be somewhere here close to the conduction band. So, this is EF and this is EC, and somewhere here will be the EV value EV, and EFI will be somewhere in the middle of EC and EV. This is my vacuum level. How do I define my vacuum level in semiconductor? This is the level where effectively the energy becomes 0, which means that all the potential energy vanishes and you are actually in free space. So, if you are able to pull an electron or a hole till the vacuum level, it effectively means that the semiconductor does not have any influence over that particle and it is basically behaving like a free particle. So, let me name one by one now. If you take this one, this is basically E times phi m, right, and from the Fermi level to the vacuum level again under no bias condition, this is E times phi s, right, and this is basically from the conduction band edge till the vacuum level is referred to as E chi. So, let me name each one of them before we move forward. So, this phi m is my metal work function, So, I will explain each one of them individually. Phi s is semiconductor work function and chi is basically referred to as electron affinity. These three fundamental units are there. What are these fundamental units? Work function for metal, work function for semiconductor and electron affinity. I will explain each one of them. What is the meaning of it? That on the metal side, the minimum energy required to pull an electron from the metal to the vacuum is referred to as the metal work function. Higher the value, more energy will be required from the metal side to be pulled towards the vacuum. Similarly, phi s is semiconductor work function, which tells me how much amount of energy an electron kept on the n side semiconductor will be required to pull up. Why I tell you an energy is required? Because see, please understand these electrons are in the lattice of the semiconductor or even in the metal, right, and they are not exactly free in terms of its energy. So, in order to make it free means that it should go to a place where net electric fields are exactly equals to 0 and there will be no force attached to it from an external world, its energy will become equals to 0. And that is the reason if you see this is an n-type semiconductor, if you would have taken a p-type semiconductor, this Fermi level would have been at the below side. E phi s will be then from the Fermi level which is below to the top side, right, and therefore, in terms of work function, if it is a p-type semiconductor, the work function will be relatively higher as compared to an n-type work function, right. That is also the case. So, in this all discussion we are assuming that the work function on the metal is larger than the work function in the semiconductor, right? And this is an ideal sort of a metal n-type semiconductor contact here. So, this is the ideal metal contact. If you look at the middle point, which is the vacuum level here, I have incidentally shown it to be sort of infinite, it is very long. So, as compared to the energies levels here and this side energy levels are relatively much higher, right. They are much higher than the left side and right hand side of the metal and semiconductor, they are much higher than that, and that is the reason we show a discontinuity here and we show that, put a dotted line here, and we show there is a discontinuity at this particular point. So, let me come now back to this thing. Now, we define two important points, that the work function is obviously the energy difference between vacuum level and the Fermi level. We have already seen this point in our diagram, and the potential difference of the contact potential is given as q times phi m minus q times chi minus V n. What is q phi f m? Q phi f. So, phi m is the energy, is the potential. If you multiply it by q, that is basically the energy. So, basically this gives you the potential, right, q times phi m, right. Phi m is the work function difference which you get. If you multiply that by q, you will get the energy, and therefore, the difference between these two will give you what is known as a contact potential, which is q phi m minus q of chi minus q V n, where q of chi is basically is defined as the electron affinity, right, on the semiconductor side, and it is measured from the bottom of the conduction band to the vacuum level. You see this one, this what I was referring to, right. This difference is defined as the electron affinity, and higher the conduction band is, lesser will be obviously the electron affinity. So, this is with the assumptions. All these metal semiconductor junction assumptions are with the fact that the interface between metal and semiconductor is very good, there is no problem in the interface, and the voltage levels are also very well defined, voltage levels are always defined to you. So, if you look at this left hand side figure here, this is under the vacuum condition which you see, and this is q phi f m as I discussed with you, this is q chi and this is q phi n, and this is basically my q v n, right. Q v n is this much. If you open up this expression here, if you open up this expression which is q chi minus q phi m, you get this q phi m minus q chi plus q v n, right. That gives you the value of the contact potential. So, the first figure here on the left hand side, which is this one, is under the condition that there is no bias being applied by an external force. So, it is perfectly in equilibrium, right. And what we are trying to say is that when you have these metal semiconductor junctions and you do not apply a bias, then the contact potential is basically the potential required for the electrons to switch from metal to the semiconductor side or vice versa, right. And we define the electron affinity as from the bottom of the conduction band to the valence band for semiconductor side. And there is a new term which I have not discussed there, but I can discuss it. It is basically QVN, which is basically the difference between EC and Fermi level. So, if you look very carefully here, this is basically your Vn as per the diagram which I have drawn here, right. So, basically if you add effectively if you add QVn with Q chi, I should get Q times phi s, which means that if Q vanishes, I get Vn plus chi electron affinity must be equals to the work function, semiconductor work function. This is on the semiconductor side. Now, this is again assuming that there are no traps, there are no impurities in the interface and so on and so forth. So, I get equation which is given by this quantity, and also I am assuming that the Fermi level is not getting displaced for whatever reasons in this condition. Now, let me take up this expression and let me explain to you what will happen if I give a bias to these. So, this was unbiased conditions. So, all these discussions were happening in unbiased conditions. That means your biasing was not there, right, unbiased conditions. However, you will also have a biased condition appearing, and let us see how it works out. So, typically if you look the value of the work function, if you look, for example, if you look at the metal side and you want to look at the work function of the metal, then let me write down some of the work function for the metal. If you look at the work function for metal, then the values comes out to be that if we take silver, aluminum, gold, chromium and molybdenum, then the values in volts will be 4.26, 4.28, 5.1, 4.5 and this is 4.6. And if we take semiconductor side, then we get germanium, silicon, gallium arsenide and aluminum arsenide, and the values for this is germanium is 4.13, silicon is 4.01, gallium arsenide is 4.07 and this is 3.5, right. And these are all the values of the work function in volts for a metal semiconductor contact. And as you can see here very interestingly that, for example, if you have aluminum silicon contact, aluminum has 4.28 and this is 4.01. So, obviously, when you match them together there will be always a discontinuity between the two, right, and that is the sort of mechanism which any metal semiconductor contact will have. So, now let me take up and give a bias onto the semiconductor side and let us see what happens. So, if we give a bias, so let me give a positive bias, this is my junction, the metallurgical junction I was talking about, this is my Fermi level on the metal side. So, this is the metal, we define this to be as Q times, let me explain to you, this is, let me write as Q times phi BO, right. So, what will happen is this Fermi level will be, let us suppose, was initially high. When you apply a positive bias onto the semiconductor side, since it is a electron energy band diagram, they will tend to make the band go down because it is minus Q times psi. So, because it is an electron energy band diagram. So, if you give a positive bias, minus Q times psi will actually push the semiconductor down, and as a result what will happen, on the semiconductor side you will see a dip and on the metal side you will not see a dip. So, what you will see is something like this. So, let me first say this is my Fermi level here, right, and then I have EV, valence band, and then this is my conduction band, correct, this is my conduction band, this is my valence band, and all the previous definitions hold good in this case, right. This we can also write down under this bias condition, this is given as Q times VBI. So, we refer to phi B 0 as the ideal barrier height, and we define phi B 0 as phi m minus chi, correct. This is basically phi m minus chi, and phi m minus chi, why? Because chi is the whole part out of which if you subtract phi m you will get phi b 0, right, this one you will get as phi b 0. And what will happen is we define V built in as phi b 0 minus phi n, this is your sort of phi n or V n, whatever I was using. So, what will happen is that Q phi b 0 will be the sum of Q V built in plus Q times phi n, and therefore, phi b 0 will be equals to V built in plus phi n. So, let us look at the V built in a much more detailed manner now. If you remember, in a MOS device, let us take, and we take n plus region and we take this n plus and this is the p type substrate, then obviously there will be a depletion region which will be formed. Depletion region will be extended more towards the p type substrate than anywhere else, and what will happen in this case is that p type substrate this. So, basically this depletion region will not allow any, if you apply a positive bias on the drain side, this depletion region will be more extended, right. Why? Because it is reverse biasing my n plus p region, and as it extends it, the depletion thickness becomes larger and larger. Please remember, in the depletion thickness the electric field is in the reverse direction. So, it does not allow any charge carriers to stay there. For example, if by some problem or another n plus region electron comes into this region, it will be thrown out of this region, right, because of the reverse bias electric field, which means that if you want the electron to cross through from this region to the p type substrate, then I require a minimum voltage of V built in, and this is known as the built in voltage. Same thing, same concept applies towards the source end also. On the source end also the same thing happens, that you require. So, this why it is important? This is important because you should understand that on the source end you generally ground it, right. So, the bias on the channel side should be at least higher to pull the electrons towards the inversion layer to form a closed path between source and drain. That is the reason V built in is quite an important sort of a parameter when we do a metal semiconductor contact. And if you look very carefully, this is where there is a variation in the energy with respect to space. We define that to be as the depletion width, and depletion width will have all donor impurities available to us plus, and these are fixed donor impurities which will be available. Understand, this is basically a metal and this is n type semiconductor. So, towards the n type semiconductor, what has happened is that the donor impurities have given electron and then themselves becomes Nd plus by application of a positive bias on the n side semiconductor, right. So, this gives you an idea about how does a metal n type semiconductor will behave. You can yourself also do it for a p type semiconductor. So, I will leave as an exercise to you that please try to go ahead and do maybe p type semiconductor with a metal, right. So, these two I will leave as an exercise for you to do it, right. Try to do it for exercise purposes, that if I have a p type semiconductor, how will I be able to formulate the n type. Now, with this knowledge or with this idea, I have already done that for reverse bias. I will extend it for reverse bias and show to you how a reverse bias and a forward bias metal semiconductor contact energy level diagrams will change. That we will take up now as an explanation. But please understand that effectively what will happen is that, and this is an intuitive one, we will take up it in the next class, that as you increase the reverse bias, more and more energy has to be spent for the charge carriers to move from one point to another, and in the forward bias it is less. So, that is the reason forward bias junctions obviously have a larger current flow, whereas reverse bias junctions have a relatively a lesser current flow. But please understand, for reverse bias the minority current carriers will actually flow very easily, and that will be basically the contribution of the minority current carrier distribution. So, in the reverse bias, so I will just take up it in the next class, but give you an idea that in a reverse bias your off currents will be generated, which will be by virtue of minority, and in forward bias it will be primarily because of I on, which will be because of majority current carriers. So, this one is minority, this one is our majority current carriers, and therefore, reverse bias are ordered smaller as compared to forward bias. Forward bias may be of the order of milliamp, whereas reverse bias is the order of few nanoamps and below, right. So, this is what the basic idea behind the metal semiconductor contact is. In the next class, we will take up the forward and reverse bias junctions, and let me recapitulate what we did now. We did a basic idea about metal semiconductor contact, the concept of electron affinity. We also understood the concept of Fermi level. So, let me write it down for you so that there is a single slide which will help you to recapitulate the whole thing. We learned the concept of homojunction, right, and we learned the concept of basic concept of heterojunction. Then we came to ohmic contacts as I discussed with you. Then we have Schottky contacts, right, contacts. Then we looked into the energy level, energy band diagrams, EBDs, for metal n type semiconductors in a general sense. And we came to the fact that how by varying the potential you can have the band diagram change towards the semiconductor side. We understood the meaning of electron affinity. We looked into work function concepts for both metal and semiconductor, right. So, this in a sense gives me the overall idea of this lecture. In the next lecture, we will take up further the reverse and forward bias of a metal semiconductor contact. Thank you very much.